So this is a presentation on the technique of point processing in medical imaging. So another way of thinking about it is it's a transformation of the grayscale intensity level. Okay, so this means that we know that an image is made up of individual pixels, and what we do when we do some processing on individual pixels is we're going to modify or transform them. We're going to do this in a way where the aim is to enhance the image quality. So other ways in which we can do it, or other names for this type of technique, are windowing. We can create a negative of an image, which has an advantage in certain situations. We can look at the histogram of the grayscale values, the pixel intensities, and then we can use these histograms to inform us to stretch those histograms and to improve the contrast in the image. And we'll also look at the technique of histogram equalization. But we can also use, and we saw this earlier in the semester, how we can use multiple images. So, for example, we can use a uniformity correction or a dark current correction of an image, where we correct each individual pixel by taking a division of two images, for example. So we'll look at this, and that what I've just described could be used. That technique of dividing two images could be used for uniformity correction. There's also background subtraction, and also the technique of averaging multiple images together to reduce the statistical noise in the imaging. So mathematically, we can think about our input image. We're going to think, remember, it's a two-dimensional function in a way. So where we have individual pixels defined by x and y, and we're going to transform this image in some way by performing some operation on each pixel to produce an output image gx of y. Okay, so we can write that mathematically, that the output image gx of y is equal to this transform operation performing on the input image, the input function fx of y. Okay, so t is an operator that's going to define. It's going to be defined over some region or neighborhood of each pixel. Okay. Okay, so mathematically this is what we mean. So here's our original input image. It's made up of lots of different pixels. We look at an individual pixel, and we're going to transform the value in that pixel to a new value, and that's going to be, that transformation is going to be done through this transformation operator t. So there's the mathematical statement again. gxy equals the transform operator on the input image. Okay, and we're going to do this transform generally. What we're going to do here is pixel by pixel. Okay, and we're going to end up with a new image where the pixel values give us a better quality image, and generally this means an improvement in the contrast in the image. So as I said, in the simplest form, this function t is going to operate on a one-by-one neighborhood, so that just means the individual pixel. But we can also do transforms in this way where we look at the neighboring pixels around an individual pixel and use that to perform the transform. But we're not going to do that here. We're going to just look at point processing, where we're just mapping individual pixels from an input image to an output image. Okay, and this function is going to transform the grey level intensity some way. Okay, through this mapping function, and in the continuous form. Okay, the output image is going to be, the output pixel value is going to be the transform on the input value of the intensity. So R here is the input intensity, and S is the intensity in the output image. Okay, so we can go through and do this for each pixel. Okay. Now, what's more likely is that it'll be a discrete function. So in that case, we'll have a discrete set of transforms for individual pixel, or we'll divide the grayscale levels up into so many levels. For example, in an 8-bit image, that would be k here would be 256. Okay, so we would have 256 transforms of the input pixel value to an output pixel value. So these are examples. So this is an example where this is the input intensity, okay, along the x-axis, and so what we can do is we take and this is the transform function t of r. So for any pixel value we can look up and we can calculate what the output pixel value would be. Okay, so for this R0 value here, the output value is going to be equal to this S0. Okay, and you can see that the effect here that R0 in this case, okay, so the input pixel value is somewhere in the middle of the range. Okay, whereas on the output image, our R0 value is going to map to this S0 value, which is up near the top of the range. Okay, so it's going to appear to be much relatively more light or bright in the image, okay, compared to in the input image. Now, the extreme case of this mapping is the binary image, so that this is basically saying that if a pixel value has a value less than some threshold, then we give it a very dark value or 0, and if that pixel value in the input value is greater than this threshold k, then it has a value of 1. Okay, so 1 and 0. So there's only two different grey levels in this output image. Okay. So remember, this is just to remind you, we can perform these transforms either on the pixel values themselves directly, or we can perform it on the lookup table. Just a reminder what we mean by lookup tables. Remember, all our pixel values are stored sort of sequentially in a particular point in computer memory. So this is the pixel value, the grayscale value in this case, and we go progressively through the image. And what we can do is we can map this pixel value to a particular color, in this case in the lookup table. So you can see the value 7 is given the color black, so that's what you can see here. So we've got 4 7s, and then we go down to the next row, we've got we've got 4 7s and then another 7, and then we've got 2 3s, which are the yellows. Okay, and then we got another black, which is 7, and then we drop down to the next level, which you can't see it, but it's red, but it's this one here. Okay, that's given the value of 1, there's that 1 there, and then we got the 2 yellows, 3 3, another red 1, and then the bottom row is 4 1s. Okay, 1 2 3 4. Okay. So this is an example of some different types of transform functions we can use, or lookup tables we can use. So you can see, typically, of course, we're going to assume here we've got 8-bit images. So that means, remember, an 8-bit image means that the grayscale value in the image can take on a value between 0 and 255. Okay. So there's our pixel value, and this function allows us to convert that into some relative brightness in this case. Okay, so whatever the pixel values, and you can see that in this particular transform there's quite a uniform sort of transform of these pixel values. It's a nice sort of straight line with a relatively it's not such a strong gradient there. Now you can see the effect if we have a much steeper gradient in our transform function. Okay, because now you can see that what's going to happen is that effectively any values below, let's say that's 60, that point there, so any values below 60 are going to be mapped to, we get all the information is in this region. Okay, so down here, any pixel values between 0 and 58 are going to have a brightness of 0. Okay, so that's dark, black. And anything sort of above, what is that going to be? It's going to be 62 or something. It's going to appear as very bright. Okay, and that's what we see in the image. What we've got here is blacks, and a lot of white, and a little bit of grey in between, and that corresponds to this part of the transform curve. We can also have different gradients in different parts of the transform. So you can see here we might have at low pixel values we have a relatively shallow gradient, and then we have a steeper gradient for this region of pixel values, and then we go for a shallower one again. And you can see that the effect that this has, remember these were originally all the same images, the effect on this output image is quite much, there's far more information in this image. I would say the contrast is better compared to this one where we have a very steep gradient on that transform function. So we can create a transform function that allows us to map these output pixel values and optimize the contrast in our output image. We can also use, this is a sort of technique where we can use what we call a double window. So we've got this is where we map grayscale values to what we do here, of course, our CT data, when we read it in, is going to be have Hounsfield units. Remember the Hounsfield unit, the definition of that is that Hounsfield unit is tells us the attenuation of the tissue in that voxel relative to water. Okay. So normally in our CT image we'll have Hounsfield unit values from -1024 all the way up to 3071. What we can do is we can say that let's assign any Hounsfield unit values from this point to this point are assigned as white, okay, and then black is given what we're doing here is that these values here are given this range, okay, scaled, and then these values also are given. So in this image, black can actually represent two different Hounsfield units. Okay, so each grayscale level in this windowing system can actually represent a higher Hounsfield unit value and a low Hounsfield unit. And we see that we can sort of emphasize features in the lungs, okay, which will be this window here. And then we have another window which is going to emphasize the bony features which we see. Okay, so quite clearly, these white features in the lung are not the same density and tissue as the bone tissue here. Okay, it's just because we've used this double windowing technique. So these are some different types of intensity transformations we can use. So here's our input intensity level. These are all sort of L here is the maximum value. There's the 3/4, half of that, quarter of that, and then 0. Okay, so typically for an 8-bit image, remember L here would be 256. Okay, so what are the main ones we've got here, the transform functions we might want to use? Well, this is the negative one. Okay, this line, you can see me tracing there. So this means that if we take let's look at the extreme value, 255. Okay. We can see that in the output image that's going to have a value of 0. So the maximum value in the input becomes the minimum value so black becomes white. And similarly, in the input image, the brightest value is going to have the lowest output value. Okay, so we've inverted and everything in between is obviously does the same, it inverts it there. That's useful in time. Other functions we can use are a logarithmic function, the nth root, the nth power, and we've got the identity where it's just a straight transform. Okay, obviously identity, that means that the input intensity level is going to equal the output intensity level, so effectively we're not performing any change there. So this shows you an example of maybe a log function we could use for transforming the pixel values. So there's our image input values, 1 plus that, C times C as a parameter we can define, and that gives us a new output pixel value. And in some situations that's going to give us improved contrast. I mentioned the negative already, so this is the negative transform function. Okay, remember this is the input intensity level, the output intensity level, so maximum of 255 is going to have a 0 on the input image. The the zero value is going to appear as very bright in the output, okay, and everything in between there is somewhere. You're just inverting it. So the effect of that, I'm sure you're all familiar with, a negative optical image. So there's the standard image, and there's the negative. So anything that's bright is now appearing as dark, and so on. Okay. We often use this in nuclear medicine. Okay, so this is the raw image here, where in this, what we're doing when we invert that, what we see is that we're going to make bone in this white, which again is sometimes useful. You can see that we can see slightly different information in this inverted image, and this is sort of, I guess, in some ways more intuitive for us, because of course in reality bone is in fact bright or white. Okay, so we can our brains are quite good at sort of looking at that and sort of interpreting the fact that there's bone there. Okay, so this negative sort of transformation is well suited when there's for enhancing white or grey detail in dark regions. Okay, because bright on dark shows up a lot better than dark on white. So we're going to be using MATLAB. So these are two functions which are useful for MATLAB. This allows us to do some sort of transform on the pixel values using this image adjust, which is the transform functions are shown here, and this is for different values of gamma. Okay, so this is a non-linear, potentially a non-linear sort of transform that allows us to map our input intensity levels to output intensity levels. So we can choose the gamma in our image adjust function. Okay, so this is our input image, but then we also have the option to give it some limits on the values that we want to perform the transform over. So these are the input low and input high, output low and output high. Now the problem is how do we know what to use here? Well, unfortunately, again, MATLAB has a function, stretch lim, I should say. So you can perform this calculation and it will calculate these two for you. Okay, it'll calculate the output low and high values of intensity that are optimal to give you the best image enhancement. Okay, so you just need to, and I think in the assessment item I ask you to sort of use this function to perform the transform on the image and to find the optimal sort of gamma values that give you the best quality or the best highest contrast in the image. Okay, moving on. So histograms. These are useful for us when we're analysing quantitatively the pixel values, the grayscale values in an image and their distribution. So a histogram, hopefully you're all familiar with a histogram. It's a plot of the probability of occurrence of each grey level. Okay, so we just divide up, we look at each grey level in the image, and then we count the number of occurrences of that grayscale level, and that gives us this probability function. Okay, so mathematically we can write it as this. So L here for an 8-bit image is going to be 256. Okay, and then we're going to, a particular pixel value, well, we can calculate it, the number of occurrences of that divided by the total. Okay, so nk here is the number of pixels of a particular grey level, rk, and n is the total number of pixels, and l is the number of grey levels. So remember, for 8-bit image it would be 256, and for a 16-bit image L here would be 64,000. I think that's a number around that. Okay. So here's some common histograms, some typical histograms, and the sort of image that they would represent. So if we had quite a dark image, we would have a histogram that looks something like this. So you can see what this means is we have a lot of pixels in our image which have a low intensity. Okay, and that's what this is showing. all the pixel values are down in this low region of the input intensity level. In contrast, a bright image has a peak that is right at the higher end. Okay, so we've got very little dark pixels in the image and a lot of bright pixels. So a low contrast image, okay, you can see would have a histogram that looks something like this. So what this means is that we have a very narrow range of pixel values that are actually used in our image. Okay, so this is undesirable. An image that has a histogram that looks something like this, where we have a narrow range of pixel values that are actually used in the image. So that will give us low contrast. And this is the opposite of that. So this is an image that has high contrast. So what you see is that all the pixel values that are available are being used effectively and have an equal number of occurrences. Okay, so this is a desirable histogram to have for an image, because it's going to give us very nice high contrast, and we're going to see how we can actually manipulate the histogram of an image into something that looks like this, and that will give us a higher contrast image. So to understand what I mean by that, well, let's look at this particular image. Okay, so it's a picture of the skull, and if we look at the grayscale values, we construct a histogram of that image. We see it looks something like this. Okay, so it's not so obvious, but there is in fact, you can see where the pointer is here, there's a very sharp peak at this low pixel value. So this means that there are a large number of pixels with very low values, which are going to be dark in the image, and that's what we see. Okay, that's all these black backgrounded pixels. Okay, these are all showing up in this peak in the histogram. Then we have the main image, and you see this is the distribution of those values. So in the actual image, part of the image that's interesting, the skull in this case, the brain, or the head, we don't have a big variation in the actual pixel values. Okay, and that's what we see in it. The image is quite low contrast. There's very little, there's not so much variation. Okay, so this peak here is corresponding to the soft tissue pixels in the image. Okay, so going back, it's this sort of a setup here. Okay, the low contrast with the narrow peak at a particular pixel value. And we can expand this a little bit here, and we can see it looks something like this. But we're not using, there's no pixels with any values up here. So we can use, there's a MATLAB function, okay, imhist, which we can use. You just have to tell it the input image, and this is the number of bins that we want. Okay, so the default is 255. Okay, so we've seen that the problem with this low contrast image and its associated histogram is that we're not making full use of all the full 255 or the full dynamic range. Okay, or for an 8-bit image that means the full range of 256 pixel values that are available to us. Okay, so in the previous image, for example, there were very few pixels with values greater than 160 and none beyond 182. Okay, so that's a zoom in of that previous the histogram of that previous image, and what we see here is that that's obvious when we zoom in on the histogram. So the following grey level transform will take the pixel values and create a histogram that makes a fuller range of display intensities, and the result will be an improvement in contrast. Okay, so remember here, RK is our input pixel value. Okay, so that's the actual grayscale value, which will have a value between, for an 8-bit image, 0 and 256. L here is the maximum number of pixel values, 256, and R max is the maximum value, okay, of the input pixel value. So by doing this, we can transform the input pixel value to an output pixel value that makes more use of the full dynamic range, so the full 256 values that are available to us. Okay. If the minimum grey level value is greater than 0, then the histogram can also be stretched at the bottom end as well. Okay, so this is just stretching it at the top. So when we want to stretch at the top and the bottom of the grayscale values in the histogram, we can just use this expression. Okay, here remember L is 256, it's the number of grayscale values in our image. R max is the maximum pixel value, R min is the minimum value, and this is the input pixel value, and then again our minimum. And that allows us to calculate for each input intensity RK an output intensity, and that's going to be stretched. That means that the grayscale values that we have used are stretched. So is that example again. Okay, there's the histogram. And this is the stretched. Sorry, this is the original image, and then this is the stretched image. Okay, so you can see that we've got a much bigger variety in the number of available pixel values, grayscale values that have been used. Okay. Now, if we zoom in on this, what we see is that the grey levels now go from 0 to 255, but what we find is they're not all used. Okay, we're missing some of the values, so we've got one at 105, 108 and 110. Okay, so this is improving things, but it's stretching them, but we're still not using all of the pixel values available to us. Okay. Another type of contrast stretching we can do is this non-linear, and this is an example. I'm going to ask you to do this in the assignment this week. Okay, so our output image is the transform function performing on the input pixel value, in this case R, and this is the function. Okay, 1 over 1 plus k, which is the particular pixel value, divided by the input image. Oh, sorry, k is a parameter that we choose, and e is another parameter that we have available to us. Okay, that's going to determine the slope. Okay, so this function here, okay, that's represented, if we plot it, it looks something like this. Okay, so this is a mapping function, so we put the input image in and we get an output image, and the pixel values have been converted. Result is that we're making more use of stretching that histogram. Okay, and this is the little bit of MATLAB script that does that. Okay, it's one. We have to be careful here to make sure we do all the multiplication or the division correctly. Sorry, so it needs to be // we have to convert the image to a double. Okay, so this calculation. So we have high precision, and then we're going to choose these parameters k and e. So histogram equalization is another technique. It's like the contrast stretching. The aim is to improve contrast by making equal use, in this case, of all grey levels. So if we go back, what we want to try and do is take the histogram of the raw image and convert the histogram into something like this, which will be higher contrast. And this histogram equalization is achieved by the following discrete transform. So the output pixel value SK is equal to L here is 256, and then we sum over the probabilities of all the individual pixels values that are available. Okay. So this sort of tries to show how that sort of works in reality. What we're trying to do is make it so that if we think about the histogram as more of a bar chart, then what we're trying to do is to ensure that for each input intensity value, so in this case going from 0 to 255, each of these rectangles, okay, these bars in the chart, has an equal area. Okay, that's what we're trying to achieve here, so that the output histogram will look something like this. Okay, where we've got it. In this case, these are the output pixel values. Okay, and their occurrence. This is the output histogram and the input histogram. So that's how we do that. And actually, if we take that histogram, if we take that histogram and we do a cumulative sum, okay, what we find is that cumulative sum is actually the transformation function. So if we've got the histogram of the transformed image, do the cumulative sum of it, we can calculate or determine this transformation function t. Okay, and we can do, I think there's a function in MATLAB called cumulative sum, or if you do a search for cumulative sum, it can take a function and calculate the cumulative sum for you. Okay, so this is just this expression here. P is the probability of occurrence. Okay. So this shows you that again there's a brain image. This is the histogram of this image, the original image. What we see is we get this big spike where we have a lot of black pixels. Okay, these are the background around it. And what we also find is that we get very few pixels with these higher values between 125 and 255 with a few white ones. Okay. So if we perform this histogram equalization, you'll notice that what we've now got is a better use in this higher region. Okay, so we've stretched this part of the histogram out to the full range over these higher values. You'll notice that it's not completely flat. Okay, but it's much better than this type of histogram. And if we look at the image, when we perform histogram equalization on it, we see we get an image like this, which is clearly, well, say clearly, I can assure you it is a higher contrast image than this, which is quite dark. Okay. But we're still, if we go back, you can see that we're still not using these values at low intensities. Okay, so the way around this is that we just perform histogram equalization over a region of the image. Okay, and you can see, so we exclude all these dark pixels when we do the histogram equalization. And the result is we get a histogram, an image that looks like this, and a histogram that is stretched out, and we're making much better use. There's more equal use of each of the intensities. Remember, this is the pixel value in the image. Okay, so we've got a way of enhancing the contrast here of this image compared to the original. So here's some just useful MATLAB functions. MATLAB does have a histogram equal function. Okay, so it will do the histogram equalization to each of the n levels. So we get an output image that's been histogram equalized with this function. Or we can actually use a histogram, so we can define a histogram that we want, and it will try and create a target histogram, and it will transform the image to try and get as close to that target histogram as possible. Okay, we're not going to do that. And the other function that's useful is this adapt histogram equalization. So this is where we do this type of thing. So we adapt the histogram, we do histogram equalization on multiple regions. So we divide it up into equal regions. Tiles, as it's called in the function, and we tell it the number of tiles that we want. Okay, so in this case, we're going to divide the image up into 16 by 16 tiles. Okay, and perform a histogram equalization on each of those tiles, regions of the image separately. Okay, so that's contrast stretching and histogram equalization, adaptive histogram equalization. I'm going to finish off by looking at point processing using more than one image, which we did look at briefly in one of the earlier sessions in the semester. I remember the work we did with the EPID images in week 8, so if you did that, then you're going to benefit here. Let's look at this image. Okay, if we look at a profile across it on this dashed line, we see that the intensity across that image varies something like that. Okay, so it's clearly non-uniform across that image. And then if we acquire another image, okay, and that's what this is. It's sort of an image with something in it. We got the structure plus this object. Okay, we get an image like this, but what you'll notice is that, and we've got the structure in the image, which you can see, which is the sort of like tennis racket. Sort of, we can see that on it, but we've got this underlying non-uniformity. Okay, so I'm trying to indicate. So we need to try and remove that non-uniformity. And the way that we do it is, so this is our image of interest, fxy. That was our non-uniformity correction image, hxy. So our output image, if we divide fxy by hxy, we get an image that has the detail in it, the structure, but it's also removed some of that non-uniformity, okay, through this division. And we're doing this division pixel by pixel, so we're taking each pixel in the input image, dividing it by the corresponding pixel and its value in the uniformity correction image. The other thing we can do is a background subtraction. So here's two images. Okay, so this is the tennis racket with a hole in it, and then we have this object behind it. So if we do a subtraction of these two images, what we're left with is the features which are different in those two, and in this case it's this region here. Okay, so this is a linear background subtraction. The other technique which is useful, and that is of image averaging. Okay, so this is where we acquire multiple images and we divide them by we add them up and we divide by the number of images we've used. Okay. So this is a single image. Okay. If we acquire 4 of those and divide by 4, okay, so we add them all up and divide by 4, we get an image that looks something like this. So you can see that the noise is reduced. Okay, it's a much smoother image. Similarly, if we go up to 16, we see a smoother image again, and then we've got this finally 256 images. It's even smoother again. So we've reduced the noise, and what we find is that the noise reduces, the signal to noise ratio is proportional to the square root of the number of frames that we use. Okay, so increasing the number of frames results in a less noisy image. We're reducing the noise in the image for the same signal. Okay, so it's a very useful technique for reducing the statistical noise. So for the same dose. Okay, so obviously in this case, let's say that each of the individual frames has a quarter of the dose. Okay, and we add them all up So the total is going to be the same dose, and then we divide by 4, and we get this nice noisy, or less noise in the summed image. Okay. So that's a bit of background to what we're going to do in this assignment 1. So this is assignment 1. It's going to be assessed. You're going to have to solve these questions, answer these questions that I'm posing in this assignment, and you're going to submit your solution in the form of a MATLAB script and a little short report with the output from the image. Okay, will you explain to me how you got these results and what they mean? So we're going to use this image skull X-ray, so it's the X-ray of a skull, available for download from Blackboard. So question 1 is to read in and display this image. Okay, and then I want you to create and plot a histogram of the image. But you're going to do that in 2 ways. One is you're going to use the MATLAB function. This is the easy way. Okay, imhist. Okay. But I also want you to write your own MATLAB function to calculate the histogram of the image, and then you're going to compare the output of this function operating on the input image compared to the image history. Okay. So remember, I showed on one of the earlier slides the expression you need to calculate the histogram of an image. You're going to do that yourselves, and then you compare it with the results of the MATLAB's built-in histogram function. Question 2 is about applying the image adjust and stretch limb functions to those images. Okay, so I want you to find the optimal parameters, the low and high brightness limits for a linear transformation of pixel values. Okay, again, go back and have a look at the notes. I'm not sure about that. And then to perform the gamma transformation. So remember the gamma transformation. No. Yep. Yes, so you're going to, I think it's this one, isn't it? You're going to use this function and you're going to find the optimal gamma that gives you the highest contrast. Okay, so you're going to do a little bit of a manual optimization there, determining the best. Yep. And then what I want you to do for each of these, display the transformed image, histogram of the transformed image, and the transformation function. Okay, so you remember how you get that. Okay, you get that from the cumulative function of the histogram. Okay, so you just need to find out how MATLAB can calculate the cumulative function. Then you're going to perform a non-linear contrast stretch, so that's using this expression. So you're going to write some script which calculates this and produces an output image which does this transform. Okay, so actually I've given it to you there. Okay, so you're going to use that. And I remember I expect this to be submitted in the form of, and you can have a single MATLAB script that answers each of these questions. So you have a progressively, a script that progressively answers the questions. So read the image in, answer question 1 in the script. Remember, it needs to be fully commented, so I know what you're doing. Then question 2, answer in the same script. 3 in the same. And then question 4 is perform a global histogram equalization on the image using MATLAB's histogram equalization function. And I want to see the transformed image and the histogram of the transformed image. And then question 5 is to do a local or adaptive histogram equalization using this adapt hist eq function on MATLAB. Okay. Again, display the transformed image and histogram of the transformed image. Okay, so your report should answer the 5 questions. You want presentation of the results in a sort of short document, okay, that has images, histograms, and a little discussion explaining your results and reasoning for optimal parameter choice. give some examples of suboptimal parameters. Okay, so that, you know, these, when I put these parameters in into this calculation, this transformation, this is a result I get. It's clearly poor contrast compared to these optimal parameters. Okay, so I want to see some sort of critical thinking here. And also well-counted source listing of your script answering the question. So put the script in an appendix to this document. Okay. The other thing is I don't want to see cut and paste of screenshots of graphs and plots and images and so on. I want you to output image files, so MATLAB is able to output to JPEG or whatever. Okay, I want you to do that. So no, if you cut and paste screenshots, you will be marked down. Okay, I want to see some nice high quality output image files that are put into your report. And I will know, it's obvious, okay, when you do this, so don't try and get away with it. Okay, so we will have a workshop session, of course, which will be an opportunity for you to get started on this, and I will be in that workshop, and I can offer you any help or answer any questions you're not sure about. Okay, thank you.